Hello, this is Adrián Galdran. I'm going to present our work for the MICCAI 2022 edition. It's on object recognition for histopathological images. You can find here the PDF and here the code for reproducing our results. So let's start because there's little time. Now, what is object recognition actually? The idea is that you train your classifier on K classes, but then at test time you can find objects or images that do not belong to any of those K classes, and then you would like your model to say, okay, I don't know what this is, and reject the classification. But many models will actually classify it happily, and that's all. So you need to build in this capability. And how do we do that? Well, we'll see. Just to see it better, an example would be you have one of those very large histology whole slide images, and you want to classify each little patch on it, okay? But this is a very complex task, so you would like to actually maybe focus on part of the categories in the slide that are of interest for you, and then you call the rest background, and you do not even bother in labeling them. Okay, so those are irrelevant tissue that you don't want to spend time labeling. Then you train your model, and you would like your model to say in test time, I don't know what this is, and reject it without ever having to train it to understand what those regions are. Now the most simple approach to this is to just train a neural network, the simplest approach, and then you just look at the output probabilities, and if they are very low, all of them, like close to a uniform distribution, and maybe this is because your image is not from any of the categories you used for training, and then you can use this for object recognition. This has been shown to be state of the art if you treat it with some care. Meaning, if you train a modern model with modern training techniques, you will end up with a model that actually produces meaningful probabilities that can be used for object recognition. Another technique that we are going to use in our work is trivial augment. The idea is very simple. It's just that you can create a data augmentation policy in which you just sample one image transformation at a time, applied with random strength, and then that's a super trivial augmentation policy that reaches the same results as other more complex learned data augmentation approaches. So in this case, we are going to use this single transform data augmentation approach to pose an auxiliary problem, which is going to be which was the data augmentation operation we applied to this image before passing it through our network. Okay, so we will ask that to our model each time we feed it an image during training. And we have all these kind of image transformations. So the idea is that since we are including the identity transform, then in test time we can take our model and use the branch F alpha for classification, which we trained as usual, but we can also ask the model which is the transformation applied to this image. In normal conditions, because the model has seen these kind of images, it will say identity. Now, if we feed the model an open set category image, an image that does not belong to any of the classes we use for training, we may expect the model to be less confident in saying identity because it has never seen this kind of tissue. So we expect our model to predict identity for known categories, and then we expect it to be very unconfident for unknown categories. And we are going to use this as our open set recognition score. Now, how do we evaluate the performance of this kind of models? First, we take one of these datasets. This is the Cather 5K dataset, and we ask our collaborators to define meaningful open-closed splits. So a closed set is the green tiles there, is the tissue of interest for us, and then the orange tiles will represent categories that are in the open set. So we do not use them for training, and we just use them for test, and expect our model to reject them. Okay. We can see that when compared with CE+, which is the state-of-the-art result I mentioned before for object recognition, also RPAR, which is a recent CVPR paper, and MC dropout, which is a very popular approach in medical imaging, we see that the AUC, which is the measure of how well your model separates closed from open set samples, is higher with our approach, and the accuracy does not suffer a lot. It's actually the highest accuracy in the second split, and it's not far from the best one in the other splits. But importantly, the AUC separating closed from open set, which is a binary problem, is highest with our approach. In a second dataset, which is larger, but still we have the same amount of splits here with different categories. We also find out that our approach gets, in 2 of the 3 cases, gets the highest AUC, and also has a reasonably high accuracy in the closed set. So, summarizing, we showed how to apply open recognition techniques to a clinically meaningful task, which is disregarding irrelevant tissue. And then we also proposed T3PO, test time transfer prediction, for open recognition in histological data, and we showed that it outperforms in some cases, in most cases, other approaches. And then a limitation would be that we are not using at all the content of the image, the semantics, the semantic meaning of the content in the tiles, in the histology, but just the color and the aspect. So that could be probably used for further improvement of our approach in more interesting scenarios. Thank you very much, and thanks for hearing me.